Hello and welcome back to a new series which is going to be called as numbers. Okay, so in this series we are going to be discussing a whole lot of basic concepts behind mathematics. Okay, so the first video today we're going to be discussing all the different types of numbers that exist, okay, in mathematics. So a few of them, let's actually go through them briefly. One of them is actually called as natural numbers. That is an actual group. Okay, a natural numbers is an actual group of numbers, which we are going to be discussing shortly. We have another number group which is called as whole numbers. Then we have another thing which is called as integers. Okay, so another group is called as rational numbers, and then we have something which are called as irrational numbers. Along with them we have something which is called as real numbers, and then we have our complex numbers. Okay, so we're going to be discussing all of these in this specific video, and afterwards we're going to be doing, positive integers, negative integers, and then we have odd numbers and even numbers, and then we also have what are called as prime numbers. Okay, so we're going to be doing that in the next video. But first of all, in this video, let's go through what our natural numbers are. Okay, so I have written like a set of natural numbers, and that basically just means in in normal plain English that the thing set basically means a group. Okay, we're just going to be going through a small group of natural numbers. Okay, so basically what natural numbers are, it's a group. Okay, so natural numbers are actually, given a specific letter in mathematics, which is a letter taken out from the English language, which is the letter N. Okay, this is the capital letter N, and this is if you actually see this in mathematical expressions, equations, or anything else, this basically it just means we are dealing with natural numbers. Okay, so these natural numbers are the following. We start with the letter, we start with the number 1, okay, and then we move on. So we have 1, 2, 3, 4, 5, and so on and so forth. Okay, so these actual 3 dots actually represent that they keep on going, they don't stop. Okay, so moving on, we also have what are called as whole numbers. Okay, so whole numbers are given the letter W. Okay, so this is the capital letter W, and this is what you are going to be you're going to go through, or you're going to basically you're going to know that this is representing whole numbers. Okay, so whole numbers actually are the following. Okay, so these are a set of whole numbers. This is the group of whole numbers, and the whole numbers actually start from the number 0. Okay, so we have 0, 1, 2, 3, 4, and then this part actually tells us that we keep on going. We have 5, 6, 7, 8, and so on and so forth. Okay, so as you can actually note down over here is that something that we have done is we have added the number 0 as a new member inside the group. This is the main difference between this specific group and the previous one which we went through. Okay, so moving on to what integers are. Okay, so this actual group is given the letter Z. Okay, this is the capital letter Z with some styly stuff on the sides, and this is actually this set actually contains the following numbers. Okay, so we have 0, and then we have positive and negative 1, and then we also have positive and negative 2, and then we have positive and negative 3, and this keeps on going. Okay, we have positive and negative 4, and so on and so forth. Okay, so this positive and negative, this specific thing basically just incorporates both of these two numbers. Okay, so this is positive 1, and then we have negative 1. Both of these are incorporated inside of this positive negative 1. And then we have, similarly, we have positive negative 3. So this is basically just stating that we have positive 3 and we have negative 3. So all that we have done over here, from which is different from the previous set and the previous group, is that we have added new members. We're just adding new members as we go on. Okay, and this time we have added all the negative numbers inside of here. Okay, so they are also becoming sort of part of the group, and this is a sort of evolving as we move on forward. So now we move on to what are called as rational numbers. Okay, so this group is not as actually, first of all, let's just go through what the letter for them is. This is the letter given to them, which is capital Q, and this is the letter given to them, and if you see this, we are probably discussing rational numbers. Okay, so this is actually not so straightforward and in in a way, because you actually have to go through this expression, which might seem daunting at first, but no worries, we'll actually go through each and every single what each and every single term means. So when we go through this specific term, and we there are actually just rules over here denoted scattered all around. So when you move through these rules and you comply with them, and then you and then you find out a number, okay, that number is going to be actually a rational number. So first of all, this perpendicular line basically just is a short way of writing in mathematics where, okay, and this x divided by y is the actual rational number, and this e is a capital E, which the symbol which looks like a capital E actually is referring to belongs to. Okay, so this is what this letter actually means. Then we have the letter Z, which again means integers. Okay, and then we have this specific symbol, which means and. Okay, and then we also have what is an equal sign, and then we have a line crossing it. So this is basically the letter does not equal. Okay, this is the equal sign, but saying that yeah, it doesn't actually equal that. Whatever is on the left hand side does not equal the whatever is on the right hand side. Okay, so this is the actual symbol. Now let's actually go through what the entire expression or the entire equation is actually telling us. Okay, so what is it actually telling us? So it's saying that if you have a rational number, it is going to be equal to p divided by q. So basically what it means that you can write it in the form of p divided by q, where p and q actually belong to integers. Okay, so the values that p and q can actually take on are the values that are containing inside of the integers set, okay, or the group of integers. You can only pick those numbers. And there is another condition which says that y cannot be equal to 0. Okay, if y cannot be equal to, or should not be, or does not equal 0. Okay, and basically what this means is that out of the integers group, q, which is also going to be equal to y, cannot be equal to 0. Okay, so this is basically what this entire equation means. Now again a short note which is basically what we have done over here is that we have just added all the decimal numbers inside of the group. Okay, first we added 0, then we added I think we added the negative numbers, and then we added, or then we're now right now we're adding all the decimals inside of decimal numbers, 4.25 or something like that. So we're adding them inside of the group. Okay, now an actual example where we use numbers instead of just the letters would be, let's say you give the values of p and q positive 4 and negative 8 respectively. Okay, so again these are both integers, we know that, and these don't actually equal to the number 0. So we actually so x divided by y, because x is actually just equal to p and y is equal to q. So we can just write x divided by y, or p divided by q, as positive 4 divided by negative 8, and simplifying that we get the answer equal to negative 1 by 2. Okay, so this is actually an example of a rational number. Okay, so negative 1 by 2 is also when you actually simplify it even further, would actually be equal to negative 0.5, which is again a decimal number. Okay, so here you can actually see that we are you just saw an actual decimal number, and basically what we're doing is just adding decimal numbers inside of our group. Now moving on, okay, to another example. 1 by 4 is equal to 0.25. This is actually another example of rational numbers. Again, over here p is equal to the number 1 and q is equal to the number 4. Both of them belong to z, and none of them is equal to the value of none of them is equal to 0. And so another example would be 6 divided by 8, which is again equal to 0.75. Okay, so none of these are actually equal to 0, and both of them belong to the integers. Okay, and I think to note down over here, only y needs to be not equal to 0. The other thing actually can be equal to 0. Okay, so moving on to what irrational numbers are. Okay, so now irrational numbers are slightly different, or you can say that all the void that rational numbers they leave, or irrational numbers actually come in to fill that void. Now irrational numbers are given the symbol the English letter capital Q again, but with a dash on top of it. Okay, so this is the main difference between irrational and rational numbers symbolically. Now, irrational numbers are a group, again, which, by following this specific, the rules given to us by this expression, you can actually find out if what you are given with is an irrational number or not. Again, this might seem daunting. We're going to go through each and every single term step by step. Okay, so starting from the left hand side, x divided by y is what is going to be called out as the irrational number in this case. Okay, and then again with the is equal sign with the dash on top of it, that basically means does not equal. And then we have our perpendicular line, which means where. Okay, and then we have our letter capital E, which is a symbol. Okay, this isn't actually the capital letter E. This is just a symbol which looks like the capital letter E, which means belongs to. And then we have Z, which means integers, and then we have this specific symbol, which is and. Okay, so what this equation is actually telling us is that what you have is an irrational number if it does not equal p divided by q. Okay, so if you cannot write your number, whatever number you have, in this specific way, which is p divided by q, okay, then you have an irrational number. Now there are specific restrictions on what p and q can actually, the values that p and q can actually take on, and then which are discussed after this perpendicular line. So which say that where p and q actually belong to integers. Okay, so p and q, both of them first of all need to belong to integers, and there is another thing over here that you need to fulfill, which is that y cannot be equal to 0. Okay, so these are the two conditions. If you can actually fulfill them and the thing cannot be written in the form of p divided by q, you have what is called as an irrational number. Okay, so some actual examples would be under root 2 or pi or under root 3. Now what is actually just happening is that this set contains all, or this group actually contains all of these numbers, all of those numbers which can't be specifically written out in decimal form. Okay, what do I actually mean by that? For example, if you have a calculator out right now, or it is actually close by, pick it up and put under root 2 or pi or under root 3 inside of them. Now what you're actually going to get is something similar to this, which is basically but even inside your calculator, you're going to have a specific number of numbers over there. And if you actually go through the internet or something, you might actually just find that all of these numbers do not actually end. They consistently keep on coming. Okay, so under root 2 basically is 1.41214. And it keeps on going. It doesn't actually have an end. Similarly, the number pi famously does not actually end, and so a few of the numbers that it contains is 3.1416 and dot dot dot. Basically it keeps on going. Similarly, we have the number under root 3. Under root 3 again does not actually stop. It keeps on going. So a few of the numbers, or actually 1 2 3 4 5, so actually to 5 significant figures, under root 3 comes out to be 1.7321. Okay, and again it keeps on going. If you actually increase the if you want to keep on going, it keeps on going. Okay, so those are all the numbers that you get in that set. Now moving on to what real numbers are. Okay, so real numbers are actually just given this symbol, given the English letter R, with a slight difference in being that they have two perpendicular lines as pillars or something for the great R, and this is the letter that real numbers are given. And real numbers actually contain this specific thing, which is basically just saying that you have let's actually go through them step by step. I would actually prefer that. So the first thing, the letter Q again is something we have recently discussed, which are rational numbers. Okay, so rational numbers. Okay, and then this letter U, or which looks like a letter U but is actually just a symbol, means union. Okay, this is an operation. This is like an operation similar to how we do the addition operation. Okay, and then we have the Q dash, which is irrational numbers. So basically what this entire equation is telling us, or the rules actually that are being discussed over that, if you follow these rules you get the real numbers, is that if you have rational numbers and if you have irrational numbers, combine them together. Okay, union is basically combining stuff together. So if you have both of these groups or both of these sets, just combine them together and you'll get real numbers. Okay, or you'll get the group of real numbers. So this is actually a really good set. It's just going out and combining other groups to make an even larger group. Okay, So this is basically what it means. So some actual real life examples would be, you know, -4/8 or pi or 1/4. And as you can see, it contains both of these things. We have rational numbers and we also have irrational numbers in this case. Okay, so this is basically all real numbers basically are. Okay, so moving on to what complex numbers are. Okay, so this is slightly different, and a lot of people actually are moving on to much more advanced courses of mathematics actually come across the complex numbers. But they're actually, you know, I just thought that, you know, let's add them into this entire conversation. So these are actually given the capital letter C as the symbol for complex numbers, and the only difference being that there is also a perpendicular line inside of the C. Okay, so this actual group contains the following numbers. Okay, so this is actually going to be so these are the rules that you need to follow to actually get what complex numbers so to get complex numbers. Okay, so basically what complex so actually just go through each individual thing first of all. So this I that you see is basically what we call as iota. Okay, and this is actually the complex portion. This is the part that actually makes the number complex. Okay, so on the right hand side, then we encounter the same perpendicular line, which means where. Okay, and then we have our capital letter with a symbol which looks like the capital letter E, which basically just means which is short of saying belongs to, and then we have the capital letter R, which is real numbers. Okay, so what is actually being told over here is that, let's say you have a complex number. Now that complex number is going to be a complex number if you have, you know, where or if you have x and y belonging to real numbers. Okay, so that is basically what complex numbers are going to be, going to be. And basically what is happening is that, you know, a complex number, the group of complex numbers is even bigger than the group of real numbers, and sort of you can actually say that, you know, it is actually trying to incorporate the real numbers into it, and as we have previously discussed, real numbers was trying to incorporate, you know, irrational and rational numbers inside of it. So this is an even bigger set, or an even bigger group. Okay, now some actual real life examples would be, let's say, you know, we use the real numbers for x and y, and we get the following results. Okay, so 2 plus 3 iota, and you can the way you actually say this is 2 plus iota 3, or you can actually say it like 2 plus 3 iota. It doesn't really matter that much. And then we have another example, -4 plus iota 0, or -4 plus 0 iota, which basically just comes out to be equal to the number -4. Okay, so moving on, we have another thing which is -5 plus iota. Okay, so this is basically all three examples, and more can actually be, more of them can actually be made if you actually follow what the conditions are, and if you follow them, and you can actually just make as many complex numbers as you want. Okay, so that is all from my side. Thank you for watching, and I really hope you learned something.